Hello everyone, welcome to the official YouTube channel of askIITians, and I am Anip Ghosh with you. In the last few sessions, I've been talking about PBlockElements, and there, I guess I have been talking about the group 13, and you have watched that video, guys, in the first part 1 specifically. Now it is the part 2 of that video where we are going to talk about the group 14 elements specifically. In the group 14 means, guys, you can clearly understand it is the carbon family, right? In the carbon family, we are talking about that carbon, silicon, germanium, tin, lead, these species. And guys, the point is, this particular part of this video would not be that much long as the group 13. It was that long because, guys, I've been telling you, we have been covering up all the important concepts of P block first in there, and all the concepts that we have learned, it is not only for group 13, it was a combination of all the P block topics together. As a result, if you haven't watched that video yet, guys, you watch that one. It's not only group 13. The first 1 hour of that video is completely based on the overall knowledge of this chapter, right? After that, we are jumping into today's session, guys. In here, we are mainly gonna focus on the same group 14 elements, but conceptually it would be nothing new to you. Everything would be known to you as we expect. And guys, here also we are going to see that inert pair effect, and due to the DNF contraction, that is also working. So I guess you guys are expecting the last element. I told you, right? Group 13, group 14, group 15, even in the next group that I'm gonna we are gonna upload in here, there also you'll be able to see the last element, like lead is today's element for us, for who would be showing inert pair effect. In the next session, it would be bismuth for group 15. So these people will be showing 2 leads valency. So there can be multiple questions coming in where lead's valency would be questioned. Let me share my screen. I believe my screen is properly visible to all of you. Let me check my voice quality real quick as well. This is on top as well. All right. So as you can see, we are talking about group 14 for the JEE people, guys. I have marked it in the last video already. Still, I'm going to show it to you one more time. If you look into the NCERT over here for the JEE mains people, starting from group 14 here, okay, you have to learn all this electronegativity, electronic configuration, all these things in here, all the way to chemical properties, reactivity towards halogen, all these things are there. Then important trends, see, I have marked it already, before the allotropes of carbon. Till that point, you have to cover it up, okay? After that, guys, we are gonna keep on going. We are gonna learn the allotropes of carbon and the rest of the part as well for the students, those who are there in JEE Advanced. All right, so let's get started for group 15. Now in group 14, guys, at least we are expecting the electronic configuration to be like NS2. Overall, the P block electronic configuration, if I see that, it would be NS2 NP126, right? So I'm not going to mention it every single time, but guys, if I'm talking about group 13, it is NP1. Group 14 would be NP2. Group 15 would be NP3. It goes on like that, right? So here, my general electronic configuration would be NS2 NP3, right? And which all elements are there? See, in group 14, we have chemistry, Sir Gibbs, Sankey problems, right? That's the way to remember all the group 14 elements. Carbon, silicon, germanium, tin, and lead. For those who like physics, guys, I believe you know these two people, like silicon and germanium are very famous for semiconductor formations, right? And there you'll learn about diodes and stuff like that, right? In there, we have learned about them. Now here, if I talk about carbon, it would be 2s2, 2p2, whereas if I'm talking about lead, 6s2, 6p2 is the general electronic configuration for this. Now, ionization. Guys, ionization energy is a topic that I've been discussing in a very detailed manner in our DNA block classes as well. That how ionization energy can never be anything other than endothermic. So it is always endothermic, right? Now, ionization energy is the energy needed to take out the outermost electron of any species, right? So let's say there is an electron in the valence shell, you want to take it out, whatever amount of energy you have to provide in that is called the ionization, right? Now you can clearly understand, more we are moving from carbon to silicon to germanium, more we are moving there, the size is increasing. The size is increasing, right? As we go down the group, the size increases always. If the size is increasing, then that, guys, it would be easier for me to take out the electrons. So ionization energy would decrease, because more you go away from the nucleus, it is going to be easier to take that electron out. It's that simple. Now, considering that, guys, we can conclude that the ionization energy order should be carbon highest, then silicon, then germanium, then as we move forward, then tin, then lead, right? This is what we expect to happen. This is our expectation. Okay. Now, guys, I am forming it in this way that is giving you a clear idea that maybe that is not how it is happening, right? Guys, see, this is something, if you have watched my PBlock first video, which is the group 13, there I have made it pretty clear. I have explained it about it in a very detailed manner. More we go from carbon to silicon, it's fine. But silicon to germanium, guys, the D block elements start coming in. And for lead, the lanthanides also pitch in. So D plus F block elements. You know what I'm talking about? Let's say this is my periodic table, right? This is where carbon is, this is where silicon is, this is where germanium. So before germanium, I have the 3D series. Science teacher, very cool, mange fair copy, nickel, copper, zinc. So the 3D series, scandium to zinc. Now, here, if I'm going for lead, in before lead, we have the 45D series, and over here we have the lanthanoids as well. Alongside lanthanoids, we have the 5D series. So lead is experiencing both the D and F block contraction. And because of that, guys, lead can show inert pair effect as well, like I have taught you in the last session. So if you are somebody who's watching this video only for group 14, and if you feel like you're not really clear about all these small topics that I'm mentioning, guys, all you have to do is just open that up video up, just watch the first 1 hour of the video. It covers up every single important topics which are there. Now moving forward with it, so we have this thing which we get to see. So as a result, the reality of the order goes like, yes, carbon is more than silicon and germanium are more or less similar, but you can see like silicon is greater than germanium, guys. You can follow the values, it is fine, you can write it. Then you are supposed to write lead and then tin, guys. Yes, lead has slightest of higher ionization energy than tin. You are gonna write this order only, although in the NCERT it is not really clear. If I am showing you the NCERT real quick, see, whatever I'm quoting, it is from the NCERT only. They haven't clearly mentioned it, but guys, it is written. See, 1086 is for carbon, then silicon, then germanium, but then we have lead and then tin, right? These orders are there in our syllabus, guys, so make sure you have gone through these values at least, right? So from there, we can come to the conclusion that the order lead goes before tin. And if I ask you why, because of D plus F contraction. Guys, D plus F contraction means because of D and F block elements, the nuclear charge on those elements like lead is very high. As a result, size is lower than you expected. As a result, guys, ionization energy is being found to be very high. That is why we see this thing happening. Now, coming to the electronegativity order. When we go to the electronegativity orders, guys, we get to see a very unique thing. First of all, what is electronegativity? This is a tendency of an atom to attract the bonded pair of electrons. Tendency to attract the bonded pair of electrons, right? That is called electronegativity. So, guys, this should be proportional to Z star. This should be proportional to the nuclear charge. So, our expectation is carbon, then silicon, then germanium. As you know, more you go down, more you go down. Acha, wait a second. Yeah, more you go down, the size is increasing because the nuclear charge is not that effective. Correct? This is the expectation that we have. Expectation. I'm just writing EX, okay? Expectation that we have. But then now, guys, if you look at the values, the reality is something different. See, carbon is the highest that we expected, but silicon, germanium, and tin have the same electronegativity value. So the order goes like this. Then silicon, germanium, and tin has the same values of electronegativity. Why, guys? Because of the decontraction. Again, you know, that decontraction is something that increases your Z star value, right? So although we are expecting that silicon after that germanium and tin's Z star value is going to go down, the nuclear charge is going to go down, the attractive forces are going to go down, but that is not really happening because of the decontraction, guys. Decontraction means d block elements cannot screen the nuclear charge, right? As a result, the nuclear charge is very, very high. Now, the most important part is, guys, where is lead? If you see, the lead is right after electronegativity order in carbon, with carbon. So carbon, lead, after that, guys, silicon, germanium, and tin has same values. This is the proper order. Remember, guys, every single values that I'm picking up over here, they are from the NCERT, so it's very, very safe to use them for your JEE Mains examination as well as board examination. Remember that, guys, for both boards and JEE Mains, NCERT is considered as the Bible. So whatever is written in the NCERT, you can use that information without any doubt. Coming to the chemical properties now. What are the five good protein elements form covalent molecules? I believe that you guys are very much well aware with my way of teaching inorganic chemistry. As guys, inorganic chemistry got a lot of things to remember, right? So as a result, what happens is I have made this entire note based on the PYQs only. All right, so all the previous year question paper of boards of JEE Advanced are all combined together in this format. As you can see, the question answer format. Yes, definitely there you see MCQ questions. So, but I have used my liberty, used my independence that to use this the questions in this way, right? So that is what you can see right now. Why the group 14 elements form covalent molecules. So what is the reason behind it, guys? It's a very simple question, isn't it? Every single time you see a question, pause this video, try to answer it on your own. So why the group 14 elements are making covalent compounds? So I guess you have tried it at least once. Now the answer to this question is because group 14 elements means carbon. Guys, in grade 9 we have learned it that carbon can neither take 4 electrons, cannot lose 4 electrons either. Because guys, the ionization energy would be too high in both the cases. Means here ionization energy, here electron. So as a result, they cannot form ionic compound. So they go for sharing of electrons. And any which ways, guys, as this is non-metals are more prone towards sharing the electrons. So that's why group 14 elements are more prone towards making the covalent species. Coming to the second question. Plus 2 oxidation increases from germanium to lead. Pause this video, give it a try first. Why is the plus 2 oxidation state is increasing? Guys, see, if I'm talking about group 14 elements, I guess you can understand your expected valency, the valency that you're expecting to happen, it is actually 4, right? Group valency should be 4 because it is 14. But here for germanium to lead, I see getting it. So carbon, silicon, germanium, tin, and lead. For carbon, we see valency 4. For silicon, we see valency 4. Germanium, we see valency 4 as well as 2. Tin also 4 as well as 2. Lead, we see only 2. Guys, this is called inert pair effect only, right? According to this concept that I taught you in the last video as well, according to this concept, because of the high Z star, high Z star. What is Z star? Nuclear charge. From where is it coming? D and F block elements cannot screen it, right? That's why it is high. For high Z star, 6s2 6p2 in this electronic configuration, 6s2 doesn't act like valence electrons. Guys, 6s2 electrons doesn't act like valence electrons anymore. As a result, this 2 configuration is only because of 6p2. But for this 4, this is 2s2 2p2. Combined together, it is 4. S and P combined together, it is 4. But here, only for the P shell, right? So that is why we see it happening. So the answer is one-stop answer is inert pair effect, right? Because of inert pair effect, we see more we go from germanium to tin to lead, as the D and F contractions are combining together. As a result, the inert pair effect is being seen. As a result, the valency of lead is being found to be. Sn plus 2 is a reducing agent, but Pb plus 4 is an oxidizing agent. Pause this video, think about it. Now, Sn plus 2 is a reducing agent. Guys, what is a reducing agent? Reducing agents are the people gets oxidized and reduces others. So it is going to reduce the other elements, and itself is going to get oxidized. As you know, guys, for tin being a group 14 element, the most stable oxidation state should be 4. So if I have Sn2 plus, it would try to convert itself into Sn plus 4. As a result, it would be losing 2 more electrons. That's why Sn plus 2 is a reducing agent. So itself is getting oxidized, right? In itself is getting oxidized, so it's a reducing. Whereas if I talk about Pb plus 4, guys, Pb, you know, the most stable valence is 2 over here because of inert pair effect. So if I have Pb plus 4, what would it do? It would try to become Pb plus 2 as soon as possible, because Pb plus 4 is not at all stable, but Pb plus 2 is, right, because of inert pair effect. So as a result, it is gonna take electrons, so it is itself getting reduced. So it's an oxidizing agent. Okay, that's how you answer this. Moving on to the next one now. Si can form SiF6 2 minus, but that's not possible for carbon. Okay, this question has a different approach actually. When we are talking about Si, in order to make SiF6, it is showing the valency. What is the valency of silicon over here? It is 6, right? Now, how is it 6? Because silicon's valency should not be 6, it should be 4 only, because it's a 14 element. Now, there you see, guys, for silicon, it is actually 3s2, 3p2 with a vacant 3d in it. Guys, in the last video, I have already told you, whenever you have a vacant d orbital, you can exceed your valency to 6. And that is what you are seeing right now. They can utilize those vacant orbitals, vacancies in those orbitals, in order to form coordinate covalent bonding. And this is what happened in this question. Whereas for carbon, guys, carbon is 2s2, 2p2. It cannot exceed its valency any further because it doesn't have a 2d orbital, correct? This is not possible. So that's why silicon, germanium also, germanium also can form GeF6 2 minus. Even tin, lead, these people, not lead, tin can also form it, right? SnH2O whole 6 2 plus. This is also formed, right? So they can show the valency of 6, but not carbon. Reactivity towards oxygen. Carbon dioxide, silicon dioxide, GeO2 are acidic, whereas SnO2 and PbO2 are acid. Why? Guys, pause this video. This is a solvable question. Now, if you try this question now, if you have tried it, so CO2, SiO2, and GeO2, if I talk about these 3 elements, guys, these are all non-metals, right? Carbon, silicon, germanium. More like metalloid character. Now, non-metallic oxides are acidic, that you already know. Example, if I talk about carbon dioxide, if I dissolve it in water, that is going to give me a carbonic acid. Carbonic acid, correct? H2CO3. So generally, we know that the non-metallic oxides are always acidic and metallic oxides are always basic. So considering these are non-metallic oxides, so we expect it to be acidic. So fine. Whereas if I talk about tin and lead, they are not yet 100% metal, right? They are like partial metallic character they have. That's why they are metallic character is what we see. So that means the moral of the story is carbon to lead metallic character increases. If the metallic character is increasing, then what would happen? Then definitely acidity would be increasing. So that means now if you want to convert a base to an acid, you have to go through the intermediate stage where the system is acting like both amphoteric, both acid and base. Then it would be turning into acidic oxides. Okay, I believe this much is clear. Now moving on to the next topic, which is which group 14 element, which elements of group 14 can form one acidic oxide commonly found in +2 oxidation state used for semiconductor. Three different questions. If I have to answer the first question, acidic oxide, I'm gonna go for carbon. Carbon can show very good acidic oxide. To answer second question, commonly found in +2 oxidation state, guys, it's a very simple question. Lead, not 4 but 2. Semiconductor, germanium, silicon. These are semiconductors, right? Okay. Reactivity towards water. Guys, remember, in this element, in this group, carbon to lead, nobody actually reacts with water. Okay. Mainly because, like for lead, there is a different reason. But first, let me talk about tin. Tin is the only one who react with water. So tin, when it is reacted with water, it forms SNO2 and hydrogen gas. Okay. So generally metals, when they react with water, they release hydrogen, correct? But there was another metal which is lead, like after that. Now lead doesn't react with water either. But why? It's a metal. Excuse me. When lead is reacted with water, what happens is you make a protective layer on the surface of the metal. And because of that protective layer, what happens is the rest of the metal is not in contact with the water anymore. So as a result, they seem like they're not reacting. Okay, but lead is capable of reacting. But due to the formation of protective layer, it cannot. It's like that. Now, reactivity towards halogen. All the tetrahalides are covalent, but SNF4 and PbF4 are ionic. Let's talk about this. Guys, all the tetrahalides means CCl4. Now, it is covalent. There is nothing new in it, isn't it? Carbon is non-metal. Covalent, right? Non-metal is covalent. But more you go down the group, you see the metallic character is increasing. Now, tin and lead, guys, they are metallic oxides. They're metallic. If they're metallic, then the non-metal, when the fluorine is a non-metal, which is connecting with it, would definitely make a ionic compound. Simple. Metal and non-metal always make ionic compound, right? PbI4 doesn't explain. It's a wrong way of asking the question. Actually, it does exist, but it breaks down immediately. Guys, it is again because of the inert pair effect. It is breaking down into PbI2 plus I2. Okay. So you should rather say like PbI4 gets decomposed into Pb plus 2 and I2. Okay. Now with the next question, which is GX4 is more stable than GX2. But PBX2, it's the same way of asking the question. PBX2 is more stable than PBX4. Guys, for germanium, the most stable oxidation state is +4 because there is no such inert pair effect on anything working. So that's why GEX greater than GX2. But when we are talking about lead, guys, lead, you know, the most stable oxidation state is +2 because of its inert pair effect. Right. So as a result, PBX2 is more stable. Okay, understood? Okay, guys, so let's go for the third question now. Except CCl4, all the other tetrahalides are easily hydrolyzed. Okay. About hydrolysis, guys, let's just go back in time a little bit. In organic chemistry, we have learned that hydrolysis is an SN1 process, right? Like where the lone pair of oxygen of water molecule they attack, correct? So if you remember that the lone pair of water is attacking agent, that means, guys, definitely it's a weak agent, correct? Lone pair is not really a strong nucleophile. It's a weak ligand or weak nucleophile, whatever you call it. That means, in a way, hydrolysis is nothing but a coordinate covalent bonding, isn't it? Because as in coordinate covalent bonding, there is a ligand and there is a, like, ligand is a donor of the lone pair. So similarly here also, the water's oxygen lone pair that is being donated, so water is acting like a ligand here, or maybe spacer, right? So now, in order to make a coordinate covalent bonding, what all criteria do we need in coordination chemistry we learned? So definitely the ligand is there. Ligand is definitely needed. But along with that, the metal in there, we need a vacant d orbital as well, right? Because that is where the ligand, let's say my water molecule, the lone pair, if it has to go and attack, it has to attack on a vacant orbital that is there. Now, here's the part. To get a vacant orbital, you need to have a vacant orbital. If you talk about CCl4 and the other halides in that group, so that means I'm talking about CCl4. Let's compare it with SiCl4 for the time being. Okay, SiCl, Cl, 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 SiCl4. And if I compare it with CCl4 right now. Now, guys, the main difference between CCl4 and SiCl4 is, as you can see, that silicon carbon is a 2s2p, right? It doesn't have any d orbital. All the orbital are taken now for this bonding. Now, Si is a 3s3p. That means it has a 3d orbital. So remember that the vacant 3d orbital, whenever you have, that is all vacant. So as a result, there is a part where they can accommodate the lone pair of water for hydrolysis process. So that's why, guys, because the presence of d orbital, we can come to the conclusion that it can undergo hydrolysis, but the CCl4 cannot undergo hydrolysis. So the moral of the story is the presence of d orbitals. The presence of the d orbitals. That is the moral of the story right now. Okay, that is the presence of d orbital is there in CCl4 and not in CCl4. That's why it doesn't undergo hydrolysis, but the others can. Simple, right? Coming to the next question now. SiF6 2 minus is known, but SiCl6 2 minus is not known. Now, what can possibly be the reason? About this method of learning, guys, see, right after this topic is over, I would suggest all of you to go to the NCERT once, right? If you go through it, you'll be able to see, in a way, we have covered up the entire NCERT as well, right? Just the approach is different. I'm not teaching you theoretically, I'm teaching you practically more of that, right? Now, this way, I believe you guys are getting it, as well as you're finding it a little simpler as well, because the concepts are all the same, just different ways of asking the question, right? But this question, guys, there is a little bit of deviation from the concept that we have been using all this time. SiF6 is known, but SiCl6 is not known, or you have to give reason, right? Now, guys, here the question, this question, as you can see, both of them are silicon. So definitely the answer is going to be with respect to fluorine or chlorine. Now, guys, the answer is very simple. What happens is when you talk about SiF6, now in this compound, fluorines being smaller in size, Silicon also is smaller in size, they can accommodate it. But when I'm going for SiCl6, you know, Cl is a comparatively bigger atom. 2, 3, 4, 5, 6. So if I talk about fluorine and chlorine, let's say fluorines are small atom, right? So here the steric effect is not that much predominant, but chlorine is comparatively bigger. So as a result, we see is there's a steric effect working in between 2Cl. Because of that reason, this compound is not stable. Okay, that is the reason behind this. Now, going to the next question. Anomalous behavior of carbon. Guys, those who are targeting for JEE mains only, this is where you stop, right? Anomalous behavior. Guys, in the very first session, I've been telling you that anomalous behavior is being shown by every single element, group's first element, right? Here also, carbon is going to show the anomalous behavior. The reasons are more or less the same. One is the p-pi bonding, and the other one is the catenation property. Okay, I'm going to tell you about both the processes one by one. First of all, guys, what is the p-pi bonding? In the very first video of group 13, I have been telling you about all the conceptual, giving you all the conceptual clarities. And there, I have been giving you this idea about as well, guys, what is the p-pi bonding, what is the p-pi bonding. Now, when we are talking about p-pi bonding, that means, guys, both the atom are using that p orbital in order to make the pi bond. That's it. So if you can see, if I talk about carbon dioxide, CO2, in here, this pi bond that we see, this pi bond is accumulated by the carbon as well as oxygen's 2p orbitals, correct? Guys, what is the electronic configuration of carbon? Electronic configuration is 1s2. I'm not drawing 1s2 all the time because it is not necessary, because it is not the valence shell, correct? 1s2, 2s2, 2p2, and oxygen is 1s2, 2s2, 2p4, right? So in this configuration, if I draw, this would be the configuration, and for 2s2, 2p4, this would be the configuration, correct? Now, when I talk about carbon in excited state and oxygen in excited state, oxygen doesn't need to go to the excited state. Oxygen alone is fine. So carbon in excited state, there'll be a electron transfer here. So as a result, the electronic configuration would become oxygen stays the same, because you cannot make more unpaired electrons out of it, right? This is all you have. Now see, guys, carbon dioxide has 2 sigma bonds and 2 pi bonds, right? See, this one is making sigma bond, this one is making sigma bond. The rest of the two are gonna make pi bond, right? So that's why, with whom is it gonna make the pi bond? See, with one carbon is making one sigma bond with the oxygen, and the other bond is pi bond with the oxygen. So if I talk about oxygen, let's call it oxygen number 1. So if I talk about oxygen number 1, see how it is making the sigma and the pi bond. So this is your sigma bond. Pairing up an electron of oxygen or an electron of carbon, we get the sigma bond. And now, similarly, with another oxygen, I have two carbons, two oxygens now, O1 and O2. Let's draw the O2 up top here. The second sigma bond, you're going to make like this with the other oxygen, O2. Now here comes the pi. So pi bonds, first, second. Guys, always remember the sigma bonds are the bonds that forms first, then the pi bonds. You cannot go like for one atom the sigma bond got formed, then the pi bond gets formed. No, first sigma bond, then if you have another atom, make the sigma bond first, then you go for the second overlapping, which is the pi bonding overlap. That's why if you notice, you are using the 2p orbital of oxygen and 2p orbital of carbon in bonding, in making both the pi bonds. Yeah, that's why we can't call it a p-pi bond, right? Now, if I talk about silicon oxygen bonding, that is p-pi-d-pi bonding that we have done in the group 13 only. Now, catenation. Catenation, so I believe all of you are pretty much aware of. If I talk about catenation property, guys, if you see for carbon, what happens for carbon is it can bind with itself. So catenation means when you can bind with yourself. Now people have a misconception that they think that catenation is only applicable for carbon, which is completely wrong, guys. Catenation is applicable for every element. Okay. Anyone who can bind with itself, that is called catenation property. So if I talk about carbon, yes, carbon can bind with itself to the maximum level. Like it can go to 400 or 500 carbons can connect with itself. But silicon also can bind with itself. 7 to 8 silicon can combine with itself. Like silicon, 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 silicon bonds. This can happen. Now, similarly for germanium also, 3 to 4 germaniums can combine with itself. So if I have to say the order of catenation, it's like self-linking property, okay guys? Order of catenation, carbon is highest, then silicon, then germanium. Tin lead doesn't really catenate. So carbon can go up to multiple values, okay? But silicon can go up to 7 to 8. And germanium can go up to 3 to 4. Carbon can do multiple. That's why carbon is the one who is being talked about all the time, right? Now, whenever we are talking about catenation property, who else can show it? Guys, even when we are making oxygen-oxygen bond, this is also catenation. Nitrogen-nitrogen bond, that is also catenation. Same elements are bonding now. So these are all catenation properties. All right. Now, coming to the next point. So we are going to talk about the elements now, guys. As you know, that there are two types of, there are allotropes, right? We learned in grade 10. Allotropes means, let's say you and I. Okay. We don't look the same, correct? Now, if you see, we are made up of the same kind of cells. You are also made up of eukaryotic cells. I'm also made up of eukaryotic cells. But why do we look different? Because the bonding inside our body, that is different. Like all the cells are not bound in the same way. That's the way it has been bound in your body. So the point is, if your building blocks are same, but your final outcome is different because the way we are bound, that is when we call it a allotropism. Allotropism means, guys, many faces. Like the humans, we are allotropes of each other, right? We have different faces, although we are made up of the same things, right? Similarly, there are many allotropes of carbon. Carbon is the building block of it, but they look different. Example, if you think about charcoal or coal, with that, if you compare graphite, guys, both of them are made up of carbon, but they look completely different based on how do they structure them, right? Now, see, I'm just going to tell you, orally about this part. So there are two types of allotropes. One is crystalline, another one is amorphous. Crystalline means crystal-like, those who have a shape. Amorphous means powder-like. Okay, you don't need all these things in detail, but I'm just going to give you this a little bit of idea first. Amorphous allotropes do not have a shape. They're like powder-like. Crystalline, they do. We learn only about the crystalline in this chapter. So there are three crystalline allotropes, as you can see. One is graphite, and other one is fullerene. Then we have this diamond as well, right? So why do they look different? Why do they show different properties? Because of their structures in the bonding side. If you notice, how is graphite gonna look like? You learned it back in grade 10th as well, guys. How do the graphite molecule looks like? So as you can see, it's a tetrahedral moiety, right? Tetrahedral species, all bonded with single bonds, right? All the atoms are bonded with single bond. Guys, remember, every one of the bonds are carbon. Every one of them are carbon. Okay, so it's a tetrahedral species. That's the first thing. Second thing is, because it is singly bonded, so it cannot conduct electricity. That's an insulator of electricity. It cannot conduct electricity. What I mean here. Because, guys, in order to conduct electricity, you have to make sure your electrons are moving. When you are singly bonded, when you're sigma bond, they cannot move their electron that much, right? Remember back in grade, this grade only, or grade 11, you can also say. In grade 11, we learned that inductive effect, right? So in inductive effect, also, we saw that inductive effect is less powerful because the sigma bonded electrons are supposed to be moved in there, right? So that's why we say the graphite is insulator, and the sigma bonded electrons, they do not move that much, right? So they're insulator of electricity. They cannot conduct electricity, but they are conductor. And these people are conductor of heat. See, in order to conduct heat, you don't need electrons or something. heat is being conducted by the vibrational motion. So this singly bonded compounds, their bonds, when they start vibrating, they can with the wave, they can kind of carry the heat waves through them, right? You know that conduction, convection, these are the methods that is there. Those are there. So diamond is a very good conductor of heat. That's why we use diamond in many transformers as well. The transformers that changes the AC to DC current, right? So there we use diamond in there, right? So these are all about this diamond structure. So guys, now if I move on to the graphite structure, you can clearly see how they are differing with each other, right? Like graphite is the hexagonal species. As you can see over here, there are many hexagons present in graphite structure, and those hexagons are sheet like, right? So like it's like one hexagonal sheet, then the second hexagonal sheet, then the third hexagonal sheet, fourth hexagonal sheet. So it's like that, right? This is one sheet, this is second sheet, this is third sheet, and all the sheets, as you can see, they are connected with each other with the help of van der Waals forces. Keystone force, divide force, London force, you know about that, right? Now here guys, that what they haven't drawn in here is we have alternating double bond like benzene. Like this. We have alternating double bonds. These alternating double bonds are the reason why they can undergo resonance, right? And that is the reason why these graphites can conduct electricity. So graphites are good conductor of electricity. So we use graphite in many electrolysis processes as well, to make electrodes with them, out of them, right? Good conductor of electricity. Okay, that's the first thing. This is also used as lubricant as well, guys. In automobile, in some other places as well, whenever you need lubricant, you can use them, because what happens is this sheet-like structure, they're movable. It's just a mere van der Waals force now. That's not powerful. So the sheets can move within each other. That is what making them a lubricating functionality in them. Okay, so that is the part about it. Okay, now coming to the fullerene structure, guys. Fullerene, see, we have a misconception about fullerene as well. See, fullerene is a structure of carbon, allotropic form of carbon, where you have a ball-like structure, correct? Made up of hexagons and pentagons. Now, the first thing that you have to understand is fullerene goes all the way up to C390, can go all the way up to 400 carbons combined together. But all of them are called fullerene, guys, okay? But C60 is called fullerene. This is known as fullerene actually, as Buckminster Fuller discovered it. As Buckminster Fuller discovered C60, that's why that is also the only one which is called fullerene. Now, guys, here we have 20 hexagons and 12 pentagons. And there's a sweet thing about them. It's like if there is a hexagon, it would be binding with both pentagon and hexagon. Okay, so if there is a hexagon, these hexagons are, it can combine with both. It can combine with both pentagon and hexagon. But the pentagons, those are there in the structure. They are only gonna combine with an hexagon. They do not combine with another pentagon. If you notice, a pentagon is always gonna combine with hexagon, but the hexagons can combine with both of them, right? So this is the thing so far about fullerene. Fullerene has a cavity in between them. That cavity is being used in order to entrap different metals, which we are going to talk about later. Going on. Okay. So this is the thing about the fullerene system. It's look like football. That's why people call it a buckyball as well. These things I believe all of you are aware of, right? Okay. Now let's go for the next very important compound of group 14, that is carbon monoxide. Guys, you are very aware of how carbon monoxide works. Even in the chapter coordination chemistry, I've seen that it's a very good ligand, right? Binding property because of the sigma donor pi acceptor capacity, right? Okay. Now coming to the part of carbon monoxide. How do we form carbon monoxide? Guys, you know that when any carbon species or any hydrocarbon species, they are being partially burned, right? So when they're being partially is oxidized, oxidized partially, that is called your carbon monoxide. We get carbon monoxide out of it. But guys, are we making in this method in industries? No. What we do is we take formic acid, we give a dehydrating agent, concentrating agent, H2SO4. If I do that, then the white marked water molecule leaves the system and you get CO out of it. This is the industrial process, industrial preparation. No, sorry, laboratory preparation. What is the industrial preparation method? Industrial preparation method is mainly we don't use CO in industries because CO is very harmful for us. What we do is, guys, in order to make CO, see, in the end of the day, in order to make any chemical substance, the major target for us is always like we are going to utilize it to make something else, right? So CO is being utilized to make a lot of things. Actually, it is a very good reducing agent. It is being used to make a lot of and numerous type of reduction CO does. So many kind of species can be formed out of it. But now the part is the way we make CO. We don't make only CO actually in industries. We make this thing. We make water gas or producer gas out of it, but the CO percentage is high. So what is water gas? Guys, this is a very common mistake that people do. When we ask them what is the formula of water gas, they think like, okay, CO is the gas, water is H2O, so let's write CO plus H2O. But that's not the reality, guys. You remember why do we call it coal gasification method? We call it coal gasification method because we take coal and then we take water vapor. That is your gas. When you combine them together, you will be getting CuNH2. So water gas is not CuNH2O, it's CuNH2. And the process is called coal gasification method. Just the same way, guys, the water gas is being formed. Actually, water gas is also known as syngas. Same thing. Why do we call it syngas? Because it is being used for synthesizing a lot of chemical reagents. Synthetic gas, that way. And what is the next one, which is the producer gas? So here you have to burn it, but in presence of the air, the atmospheric air. So in that case, this guy would become CO, but this would be there in the atmosphere, right? So CO and into this mixture is called producer gas. These are the two questions that is very often asked. Now, CO is, like I said, CO is being used in extraction of many metals. How? So, like I said, CO is a very good reducing agent. So let's say I've taken hematite. I've taken hematite. If I give CO in it, what happens is we get iron plus CO2 out of it. So just reduce the entire Fe2O3 to Fe. That means, guys, from the hematite core, I can get the pure form of iron. Right? Similarly, let's give another example. Let's say we have zincite. If I give CO in there, you get zinc and CO2. Simple. Don't try to balance the equation, guys. We are not giving you balanced equation. I'm just telling you what happens. After that, you can take some time and balance them. Okay, that is it. Now, what other reducing agent do we use in this extraction method? We use carbon, we use carbon monoxide, and we use aluminium as well. There are certain situations where we are going to use aluminium if carbon and carbon monoxide is not enough. Now the dangerous effect of CO. CO is a very good Lewis base, right? That we all know. What is making it a Lewis base? Because of this lone pair present on carbonyl carbon. That is making it a Lewis base. or you can also call it a ligand. Same thing. Now how does CO work as a Lewis space? See, CO has a lone pair, like I said, and the donation of this lone pair is possible, and as a result, it is a very good Lewis base, right? Or you can call it a ligand. Now, the best part about CO is, as you know, when the metal carbonyl complex is being done, then first CO donates the lone pair to the metal to make the sigma bond. Then the metal donates the electron back to form the pi bond. That's why CO is called sigma donor pi acceptor ligand. Pi acceptor ligand. That's why it is called sigma donor pi acceptor ligand, isn't it? Now, what actually happens is carbonyls binding tendency is near about 1,000 times greater than oxygen. Acha, binding with whom? Binding with iron. It's near about 1,000 times, 100 times to 1,000 times. So it depends on the concentration. It is like that much, enhanced, I should rather say, right? So as a result, in our hemoglobin, our main carrying species is iron only, right? Let's say this is my hemoglobin. So from there, the iron that is there, that is what binding with this oxygen to, like when you breathe in, the oxygen is being carried out forward with the iron. It binds with the iron and then it just carries away with the bloodstream, right? So now the point is, this thing gets ruptured when there is a carbonyl, carbon monoxide. So that's why in a carbon monoxide, it is like you are going to breathe in the air, but your oxygen would not reach to the cells. So the cells won't function and you would die. So that's why people call them the silent killer. Carbon is the silent killer. It's like you're going to walk through the road when there is a lot of carbon monoxide in it. You're just going to fall on the ground and you're going to die immediately. It's like that. So that's why what we do is, what we are kind of trying to say over here is, guys, that carbon is a very, very harmful agent. And because the harmfulness of carbon is due to its high binding tendency. The high binding tendency is because of its sigma donor pi acceptor nature. This is the entire moral of the story. All right? That was thing. Now, moving on to the next one, silicon dioxide. Guys, this is also known as silica. So silicon dioxide is a very, very important thing. Guys, silica is something that is being used in many, many places like water absorbent and stuff like that, right? And also known as quartz. Because the silicon dioxide is being used to make a lot of things like glass, quartz, these kind of things are being made by silicon dioxide, like SiO. Now, how do we see the silicon dioxide, bonds with each other? As you can see here, silicon dioxide is not a single bond or double bonded system. It is a cluster, right? It's a as you can see, silica clusters like SiO, SiO, SiO cluster. It just keeps on forming, right? Now here the point is, if you notice, every single bond over here, it is polar, pretty much polar, correct? So if the bond is polar, this bond should break very easily. If it can break very easily, it should be reactive. But now, if you notice, what I'm writing is silica in normal form is very, very unreactive. Why? It is unreactive because of this strong molecular cluster. It is unreactive because of its more strong molecular cluster. As we see this chain, this cluster, this like single bonded cluster, is just like diamond, guys. That's the way diamond is single bonded cluster. Similarly, silicon dioxide is also the single bonded cluster that you there. So maybe each and every bond individually are polar. They can be breakable, but because this entire structure makes it unbreakable actually. All right. Silicon dioxide, it's kind of amphoteric in nature. That you'll be able to see in the very here. Silicon dioxide, when it is being reacted with a base, it acts like an acid, and it is base, right? Now, as a result, you get sodium silicate, Na2SiO3. And when you react it with an acid, mild acid, okay, then it would be acting like a base, and then you get silicon tetrafluoride system. Now let's talk about this quartz that we can make through the silicon dioxide cluster. Quartz is a piezoelectric material. That means, guys, it is being used in formation of radio, or any kind of like electrical appliances. Long story short. Now, what is a piezoelectric material? Piezo, TV also you can write. Okay, televisions. Now, what is the piezoelectric material, guys? When you come to the advanced level of chemistry in the practicals, there is a there is a subject, I should rather say, because see, when you go to the masters or bachelors of chemistry, then chemistry breaks itself into small segments. Okay, so we have many part of chemistry. So there is one part is called the analytical chemistry. In analytical chemistry, we have a machine. We learn about the working of some machines in there, like X-ray. How does the X-ray work? How does ACM, TEM, electron microscope, these kind of thing works? Okay. So there was a machine called TEM, tunneling electron microscope, which used this piezoelectric material. So what is this piezoelectric material now? It is like when you, how should I frame it? So it's like when you are passing electricity through it now, the piezoelectric materials can change their volumes. So it changes volumes, changes volume on passing electricity through it. So if you pass electricity, then these materials would change the volume. This is also made up of quartz or silicon, right? So this is about that. Now, guys, let's talk about organosilicons. Silicones are actually organosilicon polymer, silicon polymer. Now, what do I mean by organosilicon polymer? That means silicon would be connected with some CH3 groups or some C2H5 groups, just like organometallic compounds, right? Polymer, that means you can understand, never-ending network, right? Now, how do we make them? Simple. First, we take a alkyl halide, we react it with silicon. What we get is, guys, silicon valence is 4 now. General valence is 4, can go up to 6. This compound. Now what we do is we hydrolyze it. Now, guys, I believe you know how hydrolysis works, right? First, the lone pair attacks there, the chlorine leaves the system, then you get OH in there, right? So as a result, you get, yes, OH, OH, CH3, CH3. This is what you get out of it. Now here's the part. Now, how do the polymerization happen? So, guys, you remember I taught you in biomolecules just the way glycosidic bonds are being formed. Similarly, size CH3, CH3. Then you make, okay, let's draw it down here. If I just keep on drawing this now, so I'm just drawing it with 3 of them, okay, for you to understand. You take out the water like this. Okay, if you take out the water, then the cluster would look like just like the glycosidic linkage, guys, ether linkage. This now. So it just keeps on continuing in all the both the sides. So here also, here also. That is how you get the polymeric structure of silicon. Now, let's say you are making this chain. You want to end it now. The chain is being formed. You wanted a silicon structure, which you need only 500 silicon clusters of them. Now you want it to end at 500 silicon. So what you are going to do is you are going to stop providing SiOH2. You are going to provide this guy in the structure. So it's going to be like this. Let's say this is your silicon structure. But suddenly it was happening, it was going good, 500 of them that's connected with each other. Then you give this molecule. If you give this molecule, what would happen is, see, Si, let me keep it OH in here, and let me add Si, CH3, CH3. See, the only difference over here is there are not two H anymore. There is only one H on only one side. So only this side would get polymerized, but this side won't go further anymore, right? So the polymerization chain would stop right there. So if you want to control the chain length, then you have to give this compound in the end in order to stop it. All right, that is all. Why silicons are water repellent? Very, very simple question, right, guys? If I talk about the silicon structure, although this bond is polar, you might feel like, sir, then the poly structure should be water soluble, but it is water repellent because of this alkyl group connected up top, right? So the point is water cannot reach to the silicon oxygen bond at all because this part is hydrophobic. Why is it hydrophobic, guys? Because it is organic. Why the organic compounds are hydrophobic? Because they are non-polar. CH3 is not a polar bond, right? It's a non-polar bond. That's why it is hydrophobic. Coming to the last part of silicates, guys. What are the silicates? Silicates are like silicon oxygen species which has the simplest version, which goes like SiO4 4 minus. That's the simplest version of silicate. Now, this thing, if you notice, this thing is silicate, SiO4 4, the simplest form of silicate. Now, guys, silicates are again polymeric structure. Just like silicons, silicates are also polymeric structures. Now, how do they polymerize? There are many different ways of polymerization. But before we do that, you see, try to understand, this structure is drawn in this way. Okay, so we are not going to draw it all the time in like Si and oxygen. See, silicon would be represented with a dot, and oxygens are going to be represented with a circle, right? So this is how the silicons are going to be represented from here onwards. How many types of silicons are there? Right now it's a tetrahedral structure, as you can see, right? Now have a look. How many types of silicates are there? Guys, see, this one is called orthosilicate. See, let me tell you the names first. There are orthosilicate, pyrosilicate, sheet silicate. There are many, many silicates like that. This one, as you can see, this is your orthosilicate. This is ring silicate. This, I guess, if you keep it in a chain-like structure, that is called sheet silicate. So, what is the basic difference between them? It's like silicon are combining with each other. Let's say I'm talking about orthosilicate or pyrosilicate. What happens over there is this oxygen is the reason how you are making the polymerization. That's all. If you just keep on making it, let's say this is your orthosilicate. Now you want to make a sheet silicate, so you just keep on doing this. Then it would look like a sheet, like asbestos. It's the same thing, asbestos only. So that is also made up of this part, this way only, right? If you make a ring out of it, then we call it a ring silicate, like that. Okay. So there can be many of them, but the basic structure would be SiO4 4 minus for them. Right. Now coming to the last part of this chapter, which are the zeolites. Guys, see, zeolites are actually a very, very important topic. You'll be learning it in, so you have learned it in grade 11 already. Okay. Although the hydrogen chapter has been deleted, but I'm considering if you have made it so far of this video, that means you are a JEE Advanced candidate. If you're a JEE Advanced candidate, then you haven't left that hydrogen chapter, I believe. Even if you have left it, guys, there is a part that is called softening of hard water. Okay, so you have hard water, you can make it soft water by using these zeolites in it. Okay, now how do they work? The zeolites are something like, guys, they just, if I tell you the story, hard water and soft water, the only difference is there are calcium, magnesium salts in them. If you can remove those calcium, magnesium salts out of the hard water, it becomes a soft water. Now, these zeolites, what they do is they just go inside the water, they take that calcium or magnesium salts and precipitate down. So as a result, your water can become softer. That's the entire work. Now, how do we use these zeolites, and what is the zeolite, by the way? Let's say we talk about the silicate structure. Okay, we have been talking about the silicate structures, right? Let's say suddenly we replace one of the silicon. We replace one of the silicon with aluminium. Then we are going to call that silicate structure as aluminosilicate structure, if you see in here. Aluminosilicates is what we call it. So when an aluminium replaces some silicon in the 3D silicate structure. So in the 3D silicate structure, if I replace some of the silicons with aluminium, then we get an aluminosilicate structure, and they are the actual things which are known as the zeolites. As you can see, these are the zeolites which are there. One of the most famous zeolites is ZSM5, which is used in softening of hard water. Softening of hard water. Whatever I told you guys, that's all you need to know. There is nothing much to know about these things. Just a little bit of idea about it is more than enough, right? Now I was suggesting you to go through the NCERT a little bit. From the NCERT, you give it a reading, and from there you'll be able to understand things as well. As you can see here, that the cavities, those are present in these places. These are the actually places where the magnesium or the metals, they get attached, they get entrapped. This is the place, right? So yeah, that is all about it. Now guys, I'm gonna these are the questions that you can see from the PYQs, right? So if you give it a try, all these questions are gonna be very, very simple. Okay, if you just, let's just solve a few questions in here. Let's say, this thing I just taught you. Just one second. These are from phosphorus, not from this chapter. This is group 13. Okay, let's just combine it. I believe you have watched the previous video as well, so you would be able to understand if I tell you something. Let's talk about question number 4. The number of 2-center 2-electron bond and 3-center 2-electron bond in B2H6. Guys, what was the structure of B2H6? Banana bonding, remember? And in banana bonding, there was this type of bonding. And I told you that these bonds are called 2-centered 2 electrons. So how many of them are there? 4. And these bonds are called 3-centered 2 electrons. Banana bonds are called 3-centered 2 electrons. So how many of them are there? 2. So the answer is 4 2C2E and 2C2E 3C2E. So 4 and 2. Option A is the correct answer. Okay. Now similarly, let's say we solve this question. Diborane reacts independently with oxygen and water to produce what? See guys, when it's a hydrogen system, right? When you burn it, then definitely it will form an oxide system. So the answer is B2O3. Boric, this boric anhydride, this is something I taught you in the group 13 as well. And this is something I've also told you guys. Hydrolysis of any boron species would give you boric acid every single time. So your answer is option A. Okay. Now, let's solve another question here. So if I talk about this one, aluminium is usually found in +3 oxidation state, in contrast to thallium, which is +1 and +3 oxidation state. This is due to, guys, I believe you know that the thallium shows inert pair effect. Because of that, it shows 2 less valency than the group valency. So that is it. So if you want to learn all these things, all you have to do is, guys, just watch the previous video. There I've taught about all these things in there. All right. Now let's try to solve another question here. So they're asking, where is the CT bond length maximum? Maximum means bond length is maximum, means bond order is minimum, correct? That means single bonded system. Now in diamond and graphite, we have single bonded system, right? Diamond and fullerene. Now if you see, we have diamond, we have 2 types of fullerene in here, but the fullerene structures are cyclic, correct? So definitely it's going to be acyclic things where the bond length would be the highest. So as a result, diamond would be your answer here. And what else? Basic structure of feldspar, zeolites, mica, and asbestos is silicate, right? The all feldspar, zeolite, mica, asbestos, like I told you, these are nothing but silicate structure, right? And if you do zeolite, that is aluminosilicate. Rest of them are silicate structure. So what was the silicate structure that I told you? Silicate formula SiO4 4-. So that is it, your answer. So guys, you can see that all these questions I have already taught you in here. Okay, so there is nothing that you have to worry about. Now you can go ahead and start reading from the NCERT and you can just jump into solving the questions like that. So I'm gonna sign off right now from group 14. We are gonna see each other again in group 15 video, which is gonna come right next to it. Guys, I'm gonna complete the entire P block in the same manner, in this applicable manner only, application manner only. So I believe you're finding it very, very easy so far. Yeah, there are a lot of information. I'm not really denying that fact. But then again, guys, in organic chemistry, it's all about information only, right? So you get a very straightforward question here, which you can just tick, just like we used to do in bio, right? Similarly, inorganic chemistry is a straightforward mass which you get in there. So I would suggest you guys, these are simple chapters, these are easy pick from whether you're going for JEE Advanced or JEE Mains. You are gonna be able to solve all the question if you just watch these all videos and then just go through the NCERT. You know for a fact that JEE Mains are never gonna ask you any question outside of the NCERT. So guys, let's give out 15 to 20 minutes to give it a revision from the NCERT and then go ahead and solve the questions. I believe you'd be able to solve all of them in that way. So that would be it for today, guys. See you in the next session. I'm going to upload the videos very quickly, the 15, 16, 17, and 18. I want all of you to watch this entire series of PBlock from us, right? Okay, then. So that would be it for today. Bye, everyone.